My name is Farhan Mahmud. This is Minh, that's Justin Haun, and that's Eric here. And we did a weather balloon with remote data log. Our need is that the Earth is being warmed by greenhouse gases. Recent data from the International Energy Agency shows that in 5 years' time, the climate change will be irreversible. And the current level of CO2 is 390, and at 450 is when the irreversible damage will happen. And reversal of these trends requires knowledge of this and awareness. And our device is meant to track and make people aware of this vital data. Our requirements are: we want to measure CO2, carbon dioxide, pressure, temperature, and humidity. We want to use a weather balloon to lift the package into the air. We want to comply with FAA regulations, which require the package to be under 4 pounds. And we want to broadcast GPS to retrieve the device if possible. And we want to send the cell phone data back to us and also make it resistant to the elements, weather and water. Our approach is to basically take the data from all the sensors and the GPS on the cell phone, and then send it back to us over the cell phone data, and also store it into a flash memory SD card. Our system works as such: it takes sensor data from the environment, it sends it to the microcontroller, which then generates a data file and puts it into the SD card. And also, the same data stream is sent to the cell phone, which stores it and whenever it has signal, it sends it at intervals of 5 minutes down to us. And the sensors have various ranges which do not match the full ADC range of a microcontroller. So we had to use op-amp conditioning circuits to stretch out their ranges. And also we use low-pass filters to filter out any noise. And this is an example of the temperature sensor conditioning circuit, humidity sensor conditioning circuit, pressure sensor conditioning circuit. All of these have a low-pass filter and then a non-inverting op-amp circuit to stretch out the this is the implementation of the temperature, pressure, and humidity sensor into a box. And this is the CO2 sensor, which comes calibrated to a specified range that we want, so we don't need to do any circuits for that. And we have a power distribution system where we have one 7.4-volt battery, which goes into a 5-volt regulator for the CO2 sensor, and a 3.3-volt regulator for the rest of the system, which is humidity sensor, temperature sensor, pressure sensor, and the old microcontroller circuits. And we also have 12 volts of AA lithium-ion batteries, which is to power the IO microcontroller. We're using the MSP430F2274 to process all the data, and Minh will talk about that.
The basic operations of the microcontroller can be summarized in this diagram. The microcontroller begins its operation in the idling mode, which is indicated by the LED blinking and the red flavor. When button 1 is pressed and held for 5 seconds, it will open the user interface, which will allow us to interact with the microcontroller from the laptop. We can check the sensor, configure the data settings, or connect to the data logger. If everything is working properly, we can launch the main application. The microcontroller will sample the sensor at a rate of 2 Hz, and then send the data to the data logger for storage. At 25,000 feet, the microcontroller will signal the solenoid to turn off the loop, and when the system returns to ground, you can press button 1 to put the microcontroller back to sleep. It is possible to operate the device without a laptop. The main application can be launched by pressing button 2. The communication system consists of 3 devices connected in a triangular configuration: the laptop, the microcontroller, and the data logger. And we implemented a switch to manage communication between the 3 devices. And the switch will make sure that only 2 devices are communicating with each other at any moment in time. For instance, by connecting the laptop with the data logger, we can read the data files and configure the data logger setting. extracting the sensor can be done by connecting the laptop with the microcontroller. The values for the sensor will be displayed in either hexadecimal or decimal format. And we can choose to read one single value at a time or see all the sensor values in one shot. From the main menu, we can configure the data format, the cutoff pressure, and the sample data file size. We implement a buzzer to detect data logger failure. The buzzer will make a sound if the data logger fails to launch. And we can either try to fix the data logger, or we can just launch anyway by pressing and holding button 2 for 5 seconds. This will allow the microcontroller to pump data to a backup data logger on the cell phone. And this is the format we use for the data files. It contains all the relevant information for each flight. And the rest of the file is just data with timestamps on it. And after every 45 minutes, we write to a new data file to secure the old one. And although the microcontroller is designed to work with the solenoid, we ended up not using the solenoid due to various issues.
Now we go into the cell phone part. We use an Android cell phone as the lifeline of our system. Basically the only way it can communicate wirelessly to the outside world. It has a general program flow that it takes the data from the MSP430, it goes into a device called a yo-yo, which takes this data and translates it into a form which an Android phone can understand, and then sends this data over to the phone. We take the data and parse it and combine it with GPS data, and then write it to a file. Then every 5 minutes or so, the file is sent out over the 3G network, as long as there's service. So basic way the UI for the program looks like that. Very simple. All you do is open it up and press that top button. Nothing else has to be done. And we run 2 programs on our cell phone. The first one is that one, the data logging, which I described previously, which parses and logs the data. The other program we run is an off-the-shelf program, which we downloaded for free from the App Store called Instamapper. And that thing's only function is to track GPS coordinates and send data that just tracks the phone to a website. We use the 2 different programs just in case one of them would break, the other one would still work. And they both track the phone independently of each other. Now, Android is quite complicated. There's a lot of pros and cons over using other methods for tracking, such as traditional digital analog radios or even other cell modems that you program directly. And a lot of the biggest pro is that since you have the whole Android OS managing a lot of your data communications, you don't really have to worry about programming for the cell phone network. You just have to send the data out, and you can trust that it's going to get there. So what that basically means is if you pick a good launch site and a good launch date to launch your balloon, you basically guarantee to get data back, no matter where the thing lands, as long as it is somewhere with cell service. Another big advantage is that using the GPS is quite simple. A few lines of code and you can get all the data you need and none of the stuff you don't want. And as we showed before, you can run multiple apps at the same time, for redundancy or to enable perhaps an additional feature you couldn't figure out on your own. There's also some cons that the phones are very expensive. We had to spend $250 for a phone. Programming for the IOIO can be somewhat tricky as you're programming a microcontroller in Java. Things can sometimes not work out exactly the way you would expect. So, and debugging is also somewhat complicated. There's not very good debugging tools for this kind of stuff. And the biggest con is that the Android operating system can decide to just interrupt your program whenever it wants and stop the data logging. So you have to be very careful to make sure nothing that will cause the Android OS to take over happens, like such as phone calls being received or weird things like that.
This is the overall design of the physical balloon. We'll box attach the parachute and put in by a huge water balloon. The left picture shows the water balloon guard. You have burst diameter of 6 feet, as rated on the website. And if we fill it with helium for 6 feet of diameter, you'll fly up to 100,000 feet with a 3.8-ton balloon. And the right side is the parachute. It has a diameter of 48 inches. It's rated for over 4 pounds weight of payload. And this is the design of the box. The internal size of the box is 9 times 9 times 7 inches with wall thickness of 1.5 inches. And that's the line coming out from the circuit to outside, and that's 2 housing to hold the sensors, as Farhan said earlier, and as well as sensors for. This is sporting design for the box. We have nets to wrap around the box in case you get detached from the parachute after the wind increasing on it. And let's closer look of it. And we have a warning saying if someone found it, in case we didn't find it. Saying that if someone found it, we will warn them if they call us, contact us. And this is saying that we are doing a PLM project for that reason.
So for our testing approach, we split our tests into two distinct sections: subsystem tests and device integration tests. We started off by testing and calibrating our sensors. Here you can see the calibration for our temperature sensor. And what we did was we got a known working temperature sensor, and we varied the temperature up and down and watched the voltage output from our whole sensor with its conditioning circuit and everything. And we did this a few times when we came up with the data, which is nice and linear here. And we did the same thing for humidity and pressure. We used the pressure chamber for the pressure. And the humidity, we used the then we went and we tested the microcontroller. We plugged all the sensors in and turned it on, and then wrote the microcontroller one for a while, and then we looked at the data that came out. And that all looked very good, so that test passed. Then we checked the email from the phone. We plugged everything in, turned the phone on, and see that it sends the emails correctly, and all the data's there. This is just a test from our actual launch. We're sending 8 megabyte emails every 5 minutes at this point. And inside the emails, you get data that looks a lot like this. It's just like the UART, or it's just like the microcontroller data output, except the GPS coordinates are appended onto the front. And then from here, we tried to test the box to see what kind of temperature resistance it would give us. We have a refrigerator with a -5 Fahrenheit temperature, and we started at 70 degrees. We put those thermometers in the box and left it in there for 2 hours. And after 2 hours, it came out at 20 degrees Fahrenheit. So the temperature drops significantly, but it does provide a decent amount of protection against the heat. Finally, with all these working, we decided we need to test our full system to make sure there's no strange bugs we weren't anticipating before. First, we got our whole system, put it in the box and everything, and drove it around Mason for a while. And that worked out fairly well for us. All the data worked, nothing went wrong. And after that, we had Professor Young to graciously let us use his airplane to test the box. And we did that, and things worked out fairly well. We actually did run into a couple of issues which prevented us from getting nice, perfect graphs. We were able to fix the issues finally, and then we had a real launch where we filled up a balloon and just let it go. And the results for that were clear.
So our system was launched and survived altitudes of greater than 60,000 feet, and it operated perfectly all throughout. The system sent emails with data for the first 8 minutes, after which it lost signal. And then it regained signals after about 2 hours of intense waiting. And we were able to locate exactly where it was, stuck in a tree somewhere. And then it continued running 23 hours after that, sending us larger and larger data. And here's the sensor results for pressure. We did it over time, and you can see that as time passes, the pressure drops, indicating higher altitudes, which is in accordance with theory, which suggests that the pressure in kilopascals will drop. And carbon dioxide, we have at about 390-ish out on the ground. It drops to basically nothing as it rises. And then when it lands again, it's a little bit higher than 390, which is also maybe alarming because of the global warming. And this is a theory regarding that. It confirms what we got. Basically dropped to 0 after.
Go back to that slide. Is that 20,000 feet or 2,000 feet? It goes to 0.
2,000.
Really?
Yeah, it was fast.
Wow.
There's temperature. Weirdest thing to note is that there's a bump at really high altitudes. It could be wind, jet stream, or something. And here's the temperature data. It's in accordance with what we got, with about like -55, almost -60 degrees Celsius. And here's some results for humidity. Some things to know are these sharp peaks where we believe it hit clouds, so it got a lot of moisture in the air. And to talk about our launch.
This is the area where we launched our weather balloon. It's in Eastburg, somewhere called Ida Lee Park. And we launched it at somewhere around 9:10. After 2 hours and 10 minutes flight, it landed up on Gap, Pennsylvania. And it took 104 miles to travel, and the average speed is the ground speed, 48 miles per hour. And at some point, it reached 95 miles per hour for maximum speed. And this one is the landing side of the balloon. It's a gap in the There's a huge farmland, but we are lucky enough to land on a tree that's 50 feet above the ground. This is the financial chart for our device. We spent about $1,705, including the backup. You can see now the helium costs $400 for launching the balloon.
This is the breakdown of basically the time we all reported the spending and the tasks that we were assigned in general. We kind of helped each other out, but in general, Minh did most of the microcontroller data logging programming. Farhan did all the design for the sensors and the power circuitry. Eric did the design of all the physical components, all the boxes, the soldering, the vector board layouts, all of that stuff. And I did all the cell phone data programming, the IO stuff, the video stuff. And finally, we have our lessons learned here. The first one I have is that making cutaway systems is very difficult. We tried a bunch of approaches, and we had some that worked okay, but nothing that we were confident that was actually going to work 100% up in the atmosphere. So we just got rid of it, saved the weight, saved the complexity of the system. Another one is have backups. We had a few very critical components fail at very bad times. If we didn't have backups, we would have been left out in the cold for today. I can guarantee you. And the same thing with the launch. Our first launch wasn't quite so successful. We had to have another one. And the last one is helium is expensive. It's about $150 for a tank, and you need a $125 valve just to get the helium out of the tank. And you need 2 tanks, because if you launch one balloon, it's about 3/4 of a tank. So if you mess it up, then you need to launch a second. You're going to need that second tank. And we have a video here to show.
There's Murphy's Law.
It's fun.
It's still there. We forgot to put an acknowledgements page where we'd like to thank Professor Young for letting us use his airplane, Professor Schaefer as our faculty supervisor, and Professor Packowitz for giving us a lot of advice, and for being our second faculty supervisor for lab.